Hello, my name is Danesh Shamsi and this is my Choose Your Own Adventure lab. For this report, I analyzed Felix Baumgartner's amazing jump and attempted to determine his terminal velocity. He fell all the way from the stratosphere to the surface of the Earth. As Felix fell, two important forces affected his motion. One would be the force due to gravity and the other would be the force due to drag, also known as air resistance. This is similar to the model we constructed earlier in the semester. Due to our knowledge from the previous lab, we know that Felix would reach a terminal velocity, that is, his maximum downward velocity. This happens because the force due to drag is equal to the force due to gravity, thus causing a net force equal to 0. Here, we have some initial conditions that factor into the code I constructed. We know that Felix's jump began at 39,068 meters above Earth's surface. Also, we know that the mass of Felix and his suit was equal to 117.934 kilograms. Also, some research information was that the air density at his jump height was 0.018 kilograms per meter cubed, and the air density at Earth's surface is 1.225 kilograms per meter cubed. The code itself is very similar to what was previously done, so I won't explain that in depth. Rather, I will show you the model, the graph, and tell you some interesting things that I found out from analyzing these. Here is the model I constructed. And here is the velocity time graph that was obtained from the model. You can see that terminal velocity is reached when the line becomes non-curving. By analyzing the data that was obtained from the model, we can see that his terminal velocity was about negative 372 meters per second. This is well past breaking the speed of sound. Now we'll answer some questions concerning the model I created. Question 1 asks, what model of air resistance was used and how does air density affect it? Well, I chose to use the model known as parasitic drag. This incorporates air density in addition to things like surface area. It is seen from this formula that as air density increases, the force due to drag will increase as well. As seen in the equation itself, some other factors affect the force due to drag. Now, this can also include velocity, the coefficient due to drag, and the cross-sectional area of the object that is falling itself. The velocity continually changed, so the force due to drag would also change, which would eventually equal the force due to gravity to cause a terminal velocity. I could not personally find a drag coefficient, so I had to look up some other people's analyzations of what Felix Baumgartner's jump entailed physically, and it was universally accepted that his approximate drag coefficient is 1.5. Now this is a unitless number, and it was also decided that his cross-sectional area is about 1.25 meters squared. The second question I'll answer deals with how temperature affects Felix's falling. Well, it should be noted that temperature directly affects air density. In the equation for solving for air density, which is rho in this case, temperature is in the denominator, so as temperature increases, the air density actually decreases. This means that he should actually accelerate more quickly in a warmer environment. Question 3 asks, why does he reach the speed of sound so quickly? Well, Felix breaks the sound barrier when he approximately reaches 308 meters per second. There was very little air resistance at the beginning of his fall, so he was allowed to accelerate quickly at an approximate rate of 9.6 meters per second squared due to his height above Earth's surface. Additionally, as we have learned, the speed of sound actually varies due to changes in medium. Because the temperature that high in the atmosphere was actually very low, and the air density was extremely low as well, that means that the speed of sound was much lower, so he reached it, in a sense, much more quickly than you would think.